Greetings and welcome to All by My Lonesome. I am Three Hoods, and this is my quest to figure out time travel all by myself. Last time I promised you some math, and some math you shall have, but it's going to be some weird math because this is the math of information science. In previous videos I've talked about digital signaling, where a neutral voltage represents a 0 and a positive voltage represents a 1. In information science this is called a bit. A bit is the smallest possible amount of information, which is why they're important. Bits are like the atoms of information. Even though each bit has only two possible states, as long as we have enough bits, we can represent any information. With 2 bits, we have 4 states. With 3 bits, we have 8 states. With 4 bits, we have 16 states. You can verify this yourself. Do it now. This trend continues exponentially, a statement that is literally true. 2 to the power of the number of bits is the number of possible states in the set. With 8 bits, there are 256 states, with 16 bits, 65,000 states, and with 32 bits, over 4 billion. Now, the reason I'm talking about information, bits, and states is because I'm going to use a computer to calculate time trajectories, but I have to talk to that computer somehow, and computers speak in bits, as everyone knows. So I've added this time computer to the Tesseractivator, as well as a tiny screen and some external connections, which I'll talk about in a future video. For now, I'm talking about these 2 wires. Having 1 wire for every bit I want to send isn't really a good system, so I want to send bits in sequence, one after another. Unfortunately, this is harder than it sounds. My first problem is timing. If I look at the signal voltage on a wire and I see something like this, does this represent 2 ones, a 0, and another 1? Or is it 4 ones, 2 zeros, and 2 ones? Timing has to be synchronized somehow, and it isn't enough to agree on a speed because all clocks will show some amount of drift and eventually start losing bits. The second problem is that I don't have a way to signal silence. I can signal 0 or 1, but what if I don't want to signal anything at all? Both of these problems are solved by the wart. Desktop computers used to have warts, and small embedded computers like the one I'm going to use for time travel still have them. On desktop computers, warts were replaced by USB. WART stands for Universal Asynchronous Receive Transmit, and it solves our communication problems in the following way. First of all, the 2 communicating systems agree on a base transmission speed, a word size, and a number of stop bits, also known as start bits, or stop and start bits. If you're familiar with modems, you might have seen the characters 8 and 1. Well, that 8 and 1 is a wart configuration. It means you want to use groups of 8 bits, that is to say a word size of 8 bits, no parity, which is a thing I won't talk about, and 1 stop bit. To use the system, I keep the signal line low and raise it high for an amount of time signifying my start bit. Then the 8 data bits are signaled, followed by a stop bit, and the line returns to low. Notice this means we're wasting 2 bits out of every 10, plus a small amount of time between a stop bit and the next start bit. But that's just the cost of talking to a computer. These wires connect to the time wart, and I'm going to use this device, which is a USB-powered wart, to connect it to this venerable laptop. Using a classic old-style terminal application, I can gain access to the time computer. This is a major step forward because the time computer has wireless networking and Bluetooth, so if I can power up the screen, now it can tell me its IP address, and I can set it up for remote access. From here, the possibilities are endless, up to and including time travel. So if you have a suggestion for a feature you'd like to see in the Tesseractivator when I come and visit you to bomb the virus, leave me a comment.